Today we're going to talk about the fundamental theorem of algebra. Which states that any nth degree polynomial has exactly n zeros. These zeros can be rational or irrational, real or imaginary. So for example, f of x is equal to x minus 2. It's a first degree polynomial, has 1 0, x equals 2. If you have f of x equals x squared minus 6x plus 9, you can factor this into x minus 3 times x minus 3, and you can see that this has 2 zeros because it's a second degree polynomial. X equals 3 and x equals 3. It's called a repeated root. Oops, I'm going off here. Repeated. Let's say f of x is equal to 2x squared minus 3x minus 4. You know that one has 2 zeros because it's a quadratic, it's a second degree polynomial, but you can see that this is unfactorable. So to find the zeros, you could use complete the square, but I think the easiest way is to use the quadratic formula. X equals 3 plus or minus the square root of b squared minus 4ac turns out to be 41. All over 2 times 2, which is 4. So there are 2 zeros in here, 3 plus the square root of 41 over 4 and 3 minus the square root of 41 over 4. If you have f of x is equal to x squared minus 5, that's a quick one. You know it has 2 zeros. X equals plus or minus the square root of 5. Again, 2 irrational roots. If you have f of x is equal to x squared plus 16, that's unfactorable if you consider only the real numbers, but if you can consider the imaginary numbers, you know it has 2 zeros, x is equal to plus or minus 4i. And if you wanted to really factor this using those zeros, you could factor this into x minus 4i, that would take care of the plus 4i, and x plus 4i. So if you FOILed this out, you'd get x squared plus 16 back, but this has 2 imaginary zeros. If you have a cubic, like x cubed plus 4x, this has 3 zeros. This is factorable, x times x squared plus 4, and the 3 zeros are x equals 0, and x equals plus and minus 2i, so it has 1 real and 2 imaginary zeros. If you have f of x is equal to a 4th degree polynomial, let's say x to the 4th minus 1, this has 4 zeros because it's 4th degree. And this is factorable. Difference of 2 perfect squares, x squared plus 1 times x squared minus 1. And this factor set equal to 0, you could get x is equal to plus or minus I. So there's 2 imaginary zeros, and this would be x is equal to plus or minus 1. So this has 2 imaginary and 2 real zeros, but a total of 4 zeros. If you have a 5th degree, something like f of x is equal to x to the 5th plus x cubed plus 2x squared minus 12x plus 8. You could look at the graph of that. I just put that into y equals, and I graphed it. And it looks like it has 2 times the graph is going to intersect the x-axis at x equals -2 and x equals 1. So there are 2 of the zeros, but we know there's a total of 5. So let's say we found graphically that x equals -2 is one of the zeros. So we'll pull that -2 out with synthetic division and find the resulting polynomial, just like the worksheets that we worked on in class today. 1, 0, 1, 2, -12, and 8. And going through the synthetic division, whoops, this is a -10. And then 16. And it has a remainder of 0. So the resulting polynomial is x to the fourth minus 2x cubed plus 5x squared minus 8x plus 4. And we also knew that it had, from the graph, it had x equals 1 is a second 0. So we can just take that resulting polynomial and factor out the 1 and go through this again. So with synthetic division, using that other 0, we get 1. And we get a remainder of 0. So what we have left now, this was our third degree, and this is our fourth degree, and here's our third degree polynomial. So we have x cubed minus x squared plus 4x minus 4 as a result. And if I wanted to find all of the zeros, now I've got a polynomial that we can do factor by grouping on. So we can pull out the x squared and be left with x minus 1. We can pull out the 4 and be left with x minus 1. So fully factored by grouping, x squared plus 4 times x minus 1. And then we had the x equals 1 factor from here that we can add on. And then we have the x minus equals negative 2 factor. So we can factor this all the way out with this x equals 2. And now all of the zeros here are x equals plus or minus 2i. There's 2 zeros. X equals 1. X equals 1. That's our repeated root. And x equals negative 2. So 1, 2, 3, 4, 5 total roots because it's a fifth degree polynomial. Let's say they were real nice to us and gave us a factored function. And let's say we were asked to find all zeros of f of x is equal to x minus 2 times x plus 4 raised to the third power. Now this is a fourth degree polynomial because it's a first degree times a third degree polynomial. So fourth degree has 4 zeros. And since they were so nice to us and factored this already for us, our 4 zeros are x equals 2, x equals negative 4, negative 4, and negative 4. It's repeated 3 times because it's an x to the third. So here are 4 zeros. The negative 4 is repeated 3 times because this is cubed. Sometimes we're given the zeros and we're asked to write the polynomial. So we're working in reverse. So now we're going to be writing the polynomial given one or more zeros. All right. So for example, let's say x is equal to 2 and x is equal to plus and minus 2i are the zeros. Write the polynomial. So if we wanted to write the polynomial, we can say x minus 2 is a factor because x equals 2 is a 0. X minus 2i and x plus 2i are the factors from those zeros. So if this were FOILed and simplified, we'd have x minus 2 times x squared plus 4. And then if you FOILed these together, you would just get x cubed minus 2x squared plus 4x minus 8. And there is our function, our polynomial function given those zeros. And I'll just go through a few more examples. Let's say x equals 1, x equals 3 plus I. Let's say that was the only thing given to us. And we are asked to write a third degree polynomial. All we ever have to be given if we have an imaginary root is one of the two, because imaginary roots and radical roots come in conjugate pairs. So what we have to know we have to know this, that 3 minus I is another root. So here are 3 roots, 1, 3 plus I, and 3 minus I. Well, we could set it up in factors like we did up here, but it gets a little bit complicated when you have a binomial imaginary root instead of a monomial like the example before. So what I'm going to do is take you back to Algebra 2, when you knew the roots of a quadratic equation and you were asked to write the roots of a quadratic equation, given the 2 roots, x squared minus the sum of the roots times x plus the product of the roots is equal to the function if you know the 2 roots. That's an Algebra 2 thing that we learned last year. So in this particular example, we know these 2 roots, the 2 imaginary roots, so we're going to write a quadratic equation that has those 2 roots. Well, if we wanted to add 3 plus I and 3 minus I together, we'd get 6, and 6 is the sum. If we wanted to multiply 3 plus I times 3 minus I, multiplying them, we'll get 9 minus I squared, which is equal to 10, because a negative I squared is a positive 1. So 10 is the product. So the quadratic equation having those 2 roots is f of x is equal to x squared minus the sum of the roots, which was 6, times x, plus the product. And now we also have an x equals 1. So our 3rd degree polynomial that we were asked for originally is f of x is equal to x minus 1, that's from this root, times x squared minus 6x plus 10. And we just multiply those out. So we get x cubed minus 6x squared plus 10x minus x squared plus 6x minus 10, and adding those 2 together, this multiplication will yield x cubed minus 7x squared plus 16x minus 10. And there is our 3rd degree polynomial that has the roots that we were given originally. Let's say we're given 1 root and a function, and we're asked to find all of the other roots. So let's say 1 root that we're given is x equals 5i. And we're asked to find all of the other roots of the function 2x cubed plus 3x squared plus 50x plus 75. So what we know is if we're given 1 imaginary root, we know the other is the conjugate of it, or if it's a monomial like 5i, the other root is negative 5i. So since we have 2 roots, we can either use the x squared minus the sum of the roots times x plus the product of the roots to find out the quadratic equation that has those 2 roots. Or since they're just monomials, we can say x plus 5i times x minus 5i. And that'll give us x squared plus 25. So we know 1 root. The second root is negative 5i, and there's only 1 other root because this is a cubic. So we have x squared plus 25, which is those 2 foiled together. And we want to find the other root times what is equal to 2x cubed plus 3x squared plus 50x plus 75. Well, hopefully you realize that all you have to do is divide both sides by x squared plus 25, and you'll know what that other factor is, and then you can find the other root. So you're going to have to use long division on this problem. X squared plus 25, oops, should have a placeholder of 0x plus 25. We're going to divide 2x cubed plus 3x squared plus 50x plus 75 5 by it. So we'll have 2x cubed divided by x squared is 2x. And when you subtract those, you get 3x squared. Those cancel, plus 75. 3x squared divided by x squared is 3. And when you multiply, you get 3x squared plus 75. So you have a remainder of 0. So the other factor is 2x plus 3. So the original function, fully factored, is f of x is equal to 2x plus 3 times x squared plus 25, which would give you roots that are equal to x equals negative 3/2 and plus and minus 5i. And then the last example that I'll give you, and this is the toughest one of all, let's say we're given one root is equal to 1 plus 3i. I want to find the other roots of the function fourth degree. F of x is equal to x to the fourth minus 3x cubed plus 6x squared plus 2x minus 60. So if one root is 1 plus 3i, we know the other root is 1 minus 3i because they come in conjugate pairs. One other root. And so to put those two together and make a quadratic equation, we do x squared minus the sum of the roots times x plus the product of the roots. Well, if you add those two roots, the sum is equal to 2. And if we multiply these, we get 1 minus 9i squared, which is 1 plus 9, which is 10. So there is a factor that has those two roots. So now what we're going to do is say x squared minus 2x plus 10 times what is equal to our original function x to the fourth minus 3x cubed plus 6x squared plus 2x minus 60. So what we're going to do is long division again, divided by x squared minus 2x plus 10, and we're going to find the other factor, which means we can find our other roots. So long division. And anytime you want to pause this video and try this for yourself to make sure you can do it, that would probably be helpful. All right, x to the fourth divided by x squared is x squared. And when you subtract, negative x cubed minus 4x squared, bring down the plus 2x. Divide those, you get minus x plus 2x squared minus 10x. And if you subtract those, you get negative 6x squared plus 12x, and bring down the minus 60, the last term. And then you have a minus 6. And you have a 0 remainder. So x squared minus x minus 6 is the other factor. And it is factorable. So if you wanted to factor x squared minus x minus 6, it's factorable into x minus 3 times x plus 2. So the original fourth degree polynomial that we had been given could factor into x squared minus 2x plus 10, that was the original one, times x minus 3 times x plus 2. And all of the zeros are 1 plus 3i, 1 minus 3i from this factor, x equals 3, and x equals negative 2. So we'll put the zeros down here. Zeros. X equals 1 plus and minus 3i. X equals positive 3. X equals negative 2. And you could check on your graphing calculator. The 3 and the negative 2 would have x-intercepts. And that's it for today.